Okay, gentlemen, this is part 2 of your test review. This is the chapter, I believe it's chapter 9 practice test on significance tests. I'll try to move as quickly as I can because I only have 15 minutes on these videos. All right, we've got a test of the hypotheses p equals 0.7 versus p is not 0.7, so it's a two-sided test. Sample size is 80, so our degrees of freedom are 79. And we get a test statistic of, 0.8. So maybe I don't need to worry about degrees of freedom if we're dealing with a z test. So, since it's two-sided, I have to consider everything above 0.8 and everything below negative 0.8. If I calculate one of these, I can just double it. So when I go to the calculator, I'm going to do shade normal. I'm going to do a low of 0.8 and a high of infinity, so I'm finding the right-hand tail. It's standardized. If they're giving me a test statistic, so my mean is 0, my standard deviation is 1. When I calculate that, I get an area in the tail of 0.211855. I need to double that. So the total area will be 0.4238. Right, number 2, opinion poll asks a simple random sample of 100 college seniors how they view their job prospects, and all 53 say good. So my p hat is 53 over 100. Does the poll give convincing evidence to conclude that more than half of the seniors think their job prospects are good? So we would start with a null of p equals 0.5. I can get rid of those. And my alternative is I want convincing evidence to conclude that more than half. So I want to reject the null in favor of greater than 1/2. So that's no good, that's no good. By process of elimination, my hypotheses are p equals 0.5 versus p is greater than 0.5. Didn't have to do the test. In the test of null mu equals 100 versus mu is not 100, a sample size 10 produces a sample mean of 103, and I get a p-value of 0.08. Which of the following is true at the 5% significance level? So my p-value is greater than my alpha. That tells me fail to reject. Fail to reject. There is insufficient evidence to reject, so there is insufficient evidence to conclude the alternative. D. Which of the following is not a required condition for performing a t-test about an unknown population mu? The data can be viewed as a simple random sample from the population of interest. All right, we always need that. The population standard deviation sigma is known. We only need to know sigma for a z-test. All right, let's just check the other choices. Population distribution is normal. Yeah, that is a condition where the sample size is large. The data represents n independent observations. Yeah. All 4 of the above are required conditions. No, B is not required. All right, so our answer is B. An appropriate 95% confidence interval for mu has been calculated. There it is, based on n equals 15 observations from a population with a normal distribution. So the population is normal. That satisfies the normality condition for us. If we wish to use this confidence interval to test the hypothesis mu equals 0 versus mu is not 0, which of the following is a legitimate conclusion? Now notice 0 is contained. 0 is contained in the interval. We've got a 95% confidence interval, so that coincides with a 5% significance level. So I would fail to reject. It's in there, so why would I reject? I'd fail to reject at the 5% significance level. Which of the following increases the power of a test? So power is good, right? It's the complement of a type 2 error. Decreasing the sample size, that's never going to be good. Finding a way to increase the population standard deviation, now I want to decrease that if I could, although I don't really have control over that. If I increase the significance level alpha, I'm going to increase type 1, but I'm going to decrease type 2. Decreasing the effect size. Now I want to increase. I want that to be farther away if I wanted to increase power. And using a two-tailed, now that's just going to mean more chances of error. So my answer is D. We haven't gone over how to do a two-tailed, any kind of type 2 with two-tailed. Obviously, it would be more complicated. You're going to have some stranger overlap. The infamous psychologist, Dr. Weisskopf, claims that his secret sleep tapes cause people to become better at basic algebra. All you have to do, the doctor explains, is listen to my tapes while you sleep at night, and you'll be better at algebra in 2 months. Math teacher at a local high school has expressed interest but demands evidence. 5 people are randomly selected from students at the school. They take an algebra test, listen to Dr. Weisskopf's tapes for 2 months while they sleep, then take a second test. Sounds like matched pairs. So it's a paired test if we're going to do a test. Which of the following conditions must be met in order to use a T procedure on these paired data? Now it's a very small sample size. We don't care about the pre-test and post-test. We care about the difference. All right, so if we were to do post minus pre, let's calculate that very quickly. That's what's got to be normal. Approximately normal. So it's the differences. Doesn't matter about the individual, the before or the after. Bags of a certain brand of tortilla chips claim to have a net weight of 14 ounces. That's the claim, the null. Net weights actually vary slightly from bag to bag and are normally distributed with a mean mu. A representative of a consumer advocacy group wishes to see if there's any evidence that the mean net weight is less than advertised, so intends to test these hypotheses. A type 1 error in this situation. So type 1, reject, true, null, would mean rejecting the null in favor of the alternative, so concluding that the bags are underfilled when they're not underfilled. We got it, first try. Medical researchers working on a new treatment for a standard type of cancer. After diagnosis, the average survival time on the standard treatment is 2 years. In an early trial, she tries a new treatment on 5 subjects and finds that they have an average survival time of 4 years after diagnosis. Although the survival time is doubled, the results of a t-test for mean survival time are not statistically significant, even at the 10% significance level. Which of the following is the best course of action for the researcher? Okay, well, some of our answer choices here are a little bit ridiculous. Since the test was not statistically significant, she should abandon study of this treatment and move on to more promising ones. No, that's kind of ridiculous. She should re-examine her computations. It's likely that she made an error. No, it's not. She should increase the significance level of her test so that she rejects the null hypothesis, since the treatment clearly has a positive impact. Well, it's not so clear. It's such a small sample size. And she's already using a high significance level, so she doesn't want to increase the probability of a type 1 error. She should use a z-test instead of a t-test. She can't. Her sample size is tiny. She should expand her research program to include more subjects. Yeah. Right? It was such a small sample. That's the problem. Number 10, you're testing the hypothesis that a new method for freezing green beans preserves more vitamin C in the beans than the conventional freezing method. Beans frozen by the conventional methods are known to have a mean vitamin C level of 12 milligrams per serving, so you're testing mu equals 12 versus mu is greater than 12, where mu equals the mean amount of vitamin C in beans frozen using the new method. You calculate the power of the test against the alternative, mu equals 13.5, and that power is 0.75. Which of the following is the best interpretation of this value? So remember, got to reason our way through this. Type 2 is fail to reject, false, null. Power is the complement of this. So power would be correctly reject, false, null. So let's see which of these matches. The complement of the probability of making a type 1 error. Now it's a complement of making a type 2 error. The probability of concluding that the true mean is 12 milligrams when it's actually 13.5. Well, no, that would mean we made an error if we conclude that it's 12 when it's really 13.5. So, nope. Probability of concluding that the true mean is higher than 12 milligrams per serving when it's actually 12 milligrams per serving. That's an error. No, that's not what power is. Power is good. Power is being correct. The probability of concluding that the true mean is 13.5 milligrams per serving when it's actually 12. No, that's an error. The probability of concluding that the true mean is higher than 12 when it is actually a specific value, 13.5. Yeah, that's correct. That's our power. Okay, I think I'm only going to get to one of these, so I'm going to jump down to this power, the type 1, type 2 problem. Manufacturing process is working properly. Never ready batteries have lifetimes that follow a slightly right skewed distribution with a mean of 7 hours. Quality control supervisor selects a simple random sample of N batteries every hour and measures the lifetime of each. If she is convinced that the mean lifetime of all batteries produced that hour is less than 7 hours at the 5% significance level, then all the batteries are discarded. Define the parameter of interest. Okay, mu equals the mean lifetime of all batteries produced that hour. Our null is going to be that mu equals 7, right? If she's convinced, our alternative, that it's less, mu is less than 7. Since testing the lifetime of a battery requires draining the battery completely, the supervisor wants to sample as few batteries as possible from each hour's production. She's considering a sample size of n equals 4. Seems small. Explain why this sample size may lead to problems in carrying out the significance test from A. Well, we saw in an earlier problem, when we have these tiny sample sizes, it's going to be very difficult to get statistical significance because we're only going to divide our sample standard deviation by 2. So we'd have to go pretty far away. So because of the small sample size, it's not going to be very likely to get statistical significance. All right, part C is what I really want to get to. Describe a type 1 and a type 2 error in this situation. So a type 1 error would be rejecting a true null hypothesis. So that would be concluding that the mean, remember we're making a decision here, conclude that mean, what's the wording, mean lifetime of batteries is less than 7, when in fact it is 7. Right? So that would be an error. And that would mean she would discard good batteries, discard a good batch. Type 2 error this would be failing to reject a false null hypothesis. So that would be, she concludes that the mean lifetime of batteries is 7, when in fact it's less. So the consequence is she would keep a bad batch.